This is the example in the notes, and I don't think they'll be able to hear me. Just talk to me.
This is the example in the notes.
Thank you, Charlie. Charlie made the tape today. All right. So we'll just have to go back at the end and see if my voice actually registers on this thing, and then if it didn't, I'll just trash the video. And it's back there because the way they made this room is horrible. The video input for the panel that controls that projector is back there. And in my first period class, I had 27 people, and I had people all the way back in the lab. And so I can't keep my computer up here hooked in just there. I have to hook into the system. All right, let's keep going. Let's not distract our classmates at home who aren't going to hear me. Data for the decomposition of N2O5 in a particular solvent at 45 degrees Celsius are shown. So we're talking about decomposition of N2O5, so it's N2O5 products. I don't really even care right now what the products are. I just know that it's decomposing, which means there's only one reactant. And we have a data table. So it has time, it has concentration of N2O5, and these two columns are already filled in your notes. Catch up with you really quick. Okay, so here's the data they give us, and there are two more columns that we have that are not filled out. Okay, so here's what our data table is going to look like. Now, it's kind of difficult to look at something like this in your head and figure out, is it really a straight line? Talking about concentration versus time. We have some room here. I think you have a blank graph even, right? Where we can fill this graph in. And the first step says plot the concentration of N2O5, the natural log of N2O5, and 1 over the concentration of N2O5 versus time. So 3 different graphs. The first one, concentration versus time, we already have the data. And so really you could go ahead and do that one if you wanted to. So let's go ahead and plot that out. It's going to be a lot easier on yours because you've got 3 well-defined numbers. I'm not going to really try that hard. I'm just going to give you the basic shape. The basic shape of this graph gives us enough information anyway. It doesn't look a straight line to me. And so what this could tell us is it's not 0 order anyway. Possible. Okay. Because if you're taking the natural log concentration, it's very possible. You're talking about a time of 31.28 seconds. So here's data from the natural log of the concentration. Yes, some of them are negative, that's gonna be okay, it's not a huge deal. It's just got to do with that natural log. And you can plot this out carefully. It's gonna take me a long time to plot it out carefully, so I'm just gonna go for it. It looks something like this. On my paper, it's exactly a straight line. On yours, it might be just a little bit off. So let's see, before we say that it's definitely first order, let's go ahead and do our second order graph just to verify. When I first got here to Carroll, I found this little clip-on microphone like Master would wear, and it goes to every single one of the speakers all around the room. Okay, so then we'll do my third graph, 1 over the concentration in 205, and this time it looks something like this. So I would say it was enough for curve, but we could say not second order. And so I would say, judging by the straight line, or nearly straight line, on concentration of the natural log graph, it's first order. So the next question says, write the rate law and integrated rate law for this reaction. So let me duplicate this page and I'll erase some stuff. So I'm going to erase this one because I know it's not second order, I know it's not zero order. So write the rate law. Remember what the rate law looks like? Rate equals K rate equals K times the concentration of my reactant to something. And what is my X? What's my something? The 1. It's first order, and we figured that out from the graph. So we can replace this. Now we know the rate law based from our data and our graph. Then it says write the integrated rate law. And so this one's on the AP formula sheet. The only thing we have to do is be careful not to write concentration of A. We need to write concentration of N2O5. So I'm looking at my formula sheet, and I know that this is the natural log one. Natural log of N2O5 times T minus the natural log of N2O5. 0 times 0 equals negative K times T. As long as you put in the N2O5 instead of A, now it's the integrated rate law for this reaction. Um, yeah, well, we're not even, the way we're gonna find K is actually way easier than what you're thinking right now. So that is the next question. Yeah, here we go. What is the value of the rate constant K? So the observation here is that I don't know the rate, and so it's going to be difficult to figure out using the rate law. And I don't know the initial concentration at time zero, so it's going to be difficult to use this rate law. But there was an important thing here, if you look back at your notes. This is a first order reaction, so look at the bottom of the first page, very bottom graph. It said that the slope of the straight line is negative K. We have enough data to figure out the slope. So if we use, first off, we're only using these two columns, natural log concentration and time. We can actually figure out the slope of the line pretty easily. So let's say L concentration M2O5 final minus M2O5 initial, and I don't know this sort of thing. Let's just write that delta T. This is all we have to do. It's basically like I'm using this point minus this point to find the slope. So some numbers here. So here's my slope, negative 0.0376, which means my K value is positive 0.0376, because the slope equals negative K. So negative times negative 0.0376 is positive. So the rate constant's going to have units, right? So do we even know what the units are? Let me fill in what we know. We know that the time was measured in seconds. What are your units when you take the natural log forward? I'm going to say that it is weird. So actually, here's what the units will be. Seconds to the negative 1. This is a nice thing that you could just memorize if you wanted to. When you have one reactant and it's first order, this is what your units are going to be. So I wouldn't recommend memorizing every single possibility for every units and rate laws, but for a first order reaction with one reactant, in first seconds, that's something worth maybe at least jotting a note down in the margin. What is the concentration of the concentration of N2O5 at time equals 0? Time equals 0 minutes. Okay. So let me erase some stuff here. We are looking for the initial concentration of N2O5. Can we do it? Any ideas? How about this? We use the integrated rate law to figure out the original concentration of this reaction. Because we know time is 0. K is a number, but since this is 0, it doesn't matter. And we know certain concentrations. Well, let's fill in some numbers. So for this one, actually, this is time 0, this is a different time. Let's use any of them. Just fix the last one. So the natural log of concentration in 205 at time 31.25. Actually, we don't even need that. It's just the number, we already know what it is. Minus the natural log of concentration at time 0. Equals negative. Here's our K value. And our time we're going to need is 30. Seconds. So I'm going to rely on your algebra skills and understand what I'm doing here. But add this to the other side, over that. Natural log of the concentration at time 0 equals 0.847. How do we get rid of a natural log? How does it work in our calculator? I think even, if you hit second and your natural log button, on a lot of calculators, it shows up as EPS. So if you do that, then really what that means is e to the 0.847 is my original concentration at 2.33. And units, they're just going to have to appear out of nowhere. It's a concentration. We're going to make polarity. It's magic. There was somewhere in physics this happened to. those ratings. Sometimes they appear, sometimes they just. Yeah. And we gave it a name. It was the law of disappearing and reappearing radians. I forget if it was last year. Says find the concentration of N2O5 at time equals 10 seconds. Now that you know the initial, you can do this. I think you probably could just plug in the numbers and do it. So I'm not going to put it up here. But let's go ahead and stop it there.